So first, I would like to thank everyone for coming. I would like to thank the University of Paris-Saclay to host me, the Jean committee, all the ELIS team. I'm going to show them in the next picture. The students that work on this project, lots of students work on the projects that I'm going to describe, but the students in the red color have the most important roles on the work we did in ELIS. So we brought two students. One of them is still right now here from University of Guelph, and two students from University of Paris-Saclay also worked. I should always thank actually the students, because they are the ones that do most of the work, more than 99% of the work. But also the collaborators, which without them we couldn't do the work. So Dr. Mustafavi, Chaire, and Denisov. The support, obviously, from the supporting agencies. So I found this picture on the LCP site. Without the work of the technical team that do great job here, we couldn't do any of the science, any of the experiments. One person is missing here in this picture. I don't know why Sergey is missing in this picture, but it's old. Okay. But with that, I want to go to some of the scientific applications of the nanomaterials. We have been working for years in University Mount Allison University, and later in the University of Guelph. Lots of them are applied, but we also look at the fundamental aspect of them in places like ELIS or other particle accelerators. All our fundamental science work is done at accelerators, either electron or other accelerators that I'm going to describe. So we work on magnetic nanocomposite material with applications in catalysis and environment for removing the pollutions. This is interface of different type of nanomaterial, an interface of the nanomaterial and aqueous environment. We have been working on developing solar cells. We have patents based on the nanomaterial used. This is the interface of obviously light and matter, but also different type of nanomaterial working in interface with cellulose. Photocatalysis, we developed one of the cheapest methods to make hydrogen from solar light by combination of metal oxide catalyst with polymers, organic conductive polymers, and in situ generation and probing of these. The work that I'm going to describe today is more related to biosensor and radiation therapy and some potential applications in nuclear industry. I have two collaborations, one with Sophie and one at ELIS, so one at SEA and one here. I couldn't fit the work with Sophie in the talk here, so today presentation would be interactions of nanomaterial with ionizing radiation in water, which is the work at ELIS, and some other work that is related to other external fields with nanomaterial. And we will see them. So the first part would be electron transfer reactions. Now in radiation therapy, most of the radiation damage is through the solvent. You make the hole and the electrons by ionizing radiation, and then from both of them you get different free radicals formed, and those free radicals cause the damage. But you have some direct deposition of energy in biological matter like the DNA, and that would be much less important than these, not much less from the statistical perspective. but all of these in the solvent starts with electrons. And at the beginning, a very fundamental question is that what is the electron when it is actually injected at higher energy in water and when it gets very close to thermal energy? There are calculations that suggest the electron actually is on many, many water molecules in the beginning. A few nanometer indeed could be the size of the electron. But later, this electron will get localized into solvated electron. And we are interested in both reactivity of this solvated electron and the pre-solvated electron with a nanomaterial in water. So there are two problems in the radiation therapy. One is the damage to healthy cells initiated by electrons and H2O plus making OH radical, and those cannot distinguish the healthy cells from the unhealthy cells, the cancer cells. So one is to prevent this damage. The other one is that most of the time people that have cancer and they go through radiation therapy, they have a very low immune system during the therapy because of the therapy. And unfortunately, most of the fatality is not because of the radiation therapy directly, but because of the bacterial infection or fungi infection because of this low immune system. So how to prevent this one? We started a work to address both of these. There are different strategies. I'm talking about two strategies today. One is to design a material that can react with electrons in water very fast at low concentration to avoid toxicity. It also needs to react with other radicals generated from the H2O plus, like OH radical. The compound should kill bacteria and fungi at the same time. If we can find something like this, you could use it around the tumor as a radiation shield. Or you find a material that still have some of these properties, but actually that can increase the oxidative damage by radiation in water. So very fast radiosensitizers. Cecile have worked on this for a long time here. In this case, again, you need to obviously have a low concentration to avoid the toxicity. It would be nice if the compound can also kill the bacteria and fungi so that it would prevent the other collateral damage. But if it is the case, you want to use this one in the tumor, not because that won't work as a radiation shield. How to make in my lab at Guelph, we focus on the green chemistry principles for synthesis. So lots of our work is towards the green chemistry and how to measure the activity of what you make. Here is when you need the time-resolved spectroscopy and you need an ionizing source. Mehran already described. So pulse dialysis would be ideal for these. If you have a synthesizer, so you irradiate, at least the proposed mechanism is that you irradiate it with electrons, and then most of the papers suggest that you generate further electrons from the nanoparticles, and those could cause damage. If it is protecting damage, actually, you would react with electrons and ideally with the OH radical generated from the H2O plus. We started this work long time ago, but the first published work in this series were early 2014 when we showed when we make gold nanoparticles that they won't have chemical bond to the surface So we use ionic liquids, for example, for the synthesis of them. And then you have ionic interactions, which we showed with different spectroscopic methods that there is no chemical bond, and that the interaction is ionic, not the chemical interactions. Under these conditions, you have the maximum interaction with electrons in water. Immediately after you put thiol or anything that would have any chemical bond on the gold, you reduce the reactivity. So these are the things we have shown in early 2014. So basically what we found is that you need to make the surface more accessible. And on the synthetic aspects, we focus on less work up, greener method, and at the same time make sure the surfactant would be antimicrobial. So that's why what was one of the criteria, antimicrobial, antifungi. So this, as I said, was early 2014. And then later, a group from here, Cecile actually, did some work that showed, that was late 2014, that as you increase the chemical bonds on the surface, so the surface would become less available, like when you have thiols, you have less OH production. So this is in line with our funding back in 2014. Then we decided to do look at possibility of what is this reaction of electron. Is it actually solvated electron or pre-solvated electron? The first works that we did was using another type of particle accelerator that the time scale is 0.1 nanosecond, not the picosecond that we have here. But we wanted to do some calculations to understand the molecules that react, at least reported to react with pre-solvated electron. With the rate constants in the literature, they propose close to 10 to the power 12 more per mole per liter per second, were these compounds. So we did some computation, and we found there are significant electron affinity towards this. The work was in solvent. We did density functional calculations in the solvent, and we correlated this to the free energy difference due to this reactivity. So we were convinced that, okay, we have a computational method that we can actually approach this. Then we looked at some cluster works. Smalley did very beautiful work on the metal clusters long time ago. Experimentally, actually, they measured the electron affinity of metal clusters. So we applied our calculation method to the metal clusters in the gas phase, and we found something very close to what they found in experiment. With this, we trusted more our calculations, and therefore we applied in the solvent. We found a huge electron affinity for the gold clusters, and we found that as we increase the size of the gold cluster, the affinity increases. The same experiment observed also with by Smalley's group. The other thing we found from doing electronic calculations, structures on these nanostructures, is that you cannot define orbitals on atoms anymore. So the HOMO and the LUMO is actually distributed on the whole nanostructure. What it means is that these individual atoms, quantum mechanically, you cannot distinguish from each other. What is important is a big electronic structure on the whole system. So it's like a mega atom that you have. So these are computational works. Now, if we assume that the reactivity is, because the electron affinity is huge compared to these, the reaction at best should be, at lowest should be diffusion controlled, even if ignore the quantum tunneling. if you assume diffusion control, just because of the size, it's much larger. The rate constant that you get is starting for 1 angstrom for the small particles, the small compounds that I showed you, and going to 20 nanometer, you start getting something around 10 to the power 15 per mole per liter per second. This is just bigger size, bigger target. You hit it easier. And then we predicted that the rate would increase with size. Now, this only could happen, and we observed this, and I will show you how we observed it later, for whenever the surface is available. And when you have chemical bond, the surface is not as much available, like in the case of tiles, but when you have ionic material in the water, they are fluffy, they can move around, and then you get a more available surface. I think the same would happen with the polymers. So the first work was in early 2014, but later in 2015, we did extra work after calculations and look at the temperature dependence of this. So we didn't have access to electron beam at that time. We have something similar to the proton beam. Let's assume that you have high energy proton in liquid. What will happen to that high energy proton? Eventually, that high energy proton will cause ionization and then capture one of the electrons and form a hydrogen atom. Now let's say one of these protons, we can label it and call it a red proton among all of the other protons that you have in the solution, like in water. That red proton makes a red hydrogen atom, or it could react with water to give to add to the lone pair of the this, like H3O plus with a red proton, right? It could react with the salvated electron to form hydrogen atom, or it could have a hydrogen transfer, proton transfer. And if it has a proton transfer, it gets trapped into a diamagnetic molecule. So this H atom is paramagnetic, this is diamagnetic. If you have something that could react, like a scavenger that could react with this hydrogen atom, you form another radical, which is also with unpaired electron. Now, in addition to this, you have an opportunity for the electron to react with the gold nanoparticle. So this combination is the important thing to consider. If we had this red proton, then we could distinguish the formation of the hydrogen versus this diamagnetic species from each other because we could label them, right? A labeled proton. Can we have something like a labeled proton, a red proton? We have. Positive muons is one of the fundamental particles in the nature with the same charge as the proton, the same spin. So that means if you put them in a magnetic field, they behave the same as the proton, almost, if you correct for the magnetic moment, which depends on their mass. The main difference other than this is that they are short-lived, so around 2 microsecond lifetime. This is bad because that means you cannot do something which is long lifetime. You cannot study them, but it's good for the short lifetime species because we can probe the short lifetime species with these positive muons. A positive muon therefore behaves like a light proton. And due to the weak interactions, you get 100% spin polarization. Now, in NMR or electron spin resonance, we get the Boltzmann distribution. And if you use particle counting techniques like in accelerators, then the sensitivity is billion times more than ESR or NMR. So extremely sensitive. We can even do experiment with 1 muon in Avogadro number of the molecules and detect the formation of the hydrogen atom equivalent under those conditions. I'm not going into much details of this weak interaction because later this month or next month we will have a workshop that I'm going to describe those. But I described one of our aspects of the muon techniques. The positive muon would come in this direction. The spin is antiparallel to the direction of the incoming muon, the momentum. And as it passed through a detector, it generates an electronic signal. Eventually, it would stop in the sample. It would thermalize, go to the thermal energy. Along the way, it generated the electrons. It would form as diamagnetic that I showed you, or a paramagnetic species. And if you put a magnetic field, depending on what is the nature of these species, the precision, very much like FID signal in NMR, you have a spin precision. And if you correct for the lifetime, natural lifetime of the muon, then you get asymmetry in the detection in this particle detector compared to this one. If there is no reaction for this species, it would just oscillate. If there is a reaction, this would decay with time. So some of the features of these methods. First, we don't need optical window because we deal with the magnetic measurements. The second is that it's very similar to NMR. So it provides information on electronic structure, but for reactive intermediates. That means for free radicals. We can find electronic structure of these radicals. And the fact that we don't have need optical window is giving us the conditions that we can study from basically 0.1 Kelvin, or actually lower than that if you want, under any pressure, any pressure that we want, to high temperatures and high pressures. The high pressure, high temperature, we have limits. The maximum limit in our group we achieved is close to 650 degrees centigrade and 250 bar. Actually, really right now 600 centigrade, but we are achieving 650 and 250 bar. And as you go to a lower temperature, we can go even to higher pressure. These sort of experiments are important for the nuclear reactors, obviously, because they are working under high pressure. So when that positive muon captures an electron, I told you it's a red hydrogen atom, so that means a labeled hydrogen atom. But there is a difference. You have, instead of proton, a muon as a nuclei. For chemists, what is important for the electronic structure and reactivity is not much mass, but the reduced mass. The reduced mass, if you calculate, is almost the same as hydrogen atom. The ionization potential as a function of reduced mass is the same, almost. And Bohr radius is the same within the two decimal points. So that means really we have a red hydrogen atom that we can detect in the middle of 10 to the power 23 molecules. Now, for any free radical, like a hydrogen atom, you have the bright, if you put the magnetic field, because of the coupling of the electron to the nuclei, if you go to different fields, you can actually have two different spin precisions that would cause a splitting of the signals that you see in time domain. And from this splitting, you get the hyperfine coupling, and hyperfine coupling is proportional to electron density at nuclei. So indeed, if we have a radical, and we did even a case to the largest one, C70 so far, we could map out the electron density at all of the nuclei in the C70 experimentally with this technique. It takes a long time, but we can do that. So now the results of our experiments in the presence of gold nanoparticle was that actually we don't see any of these muonium formed when you put gold nanoparticle in water. How do we know that it's not formed? As I told you, you have a splitting of the muon signals, spin precisions, and this splitting would show into this bitting frequencies. Or if we go to frequency domain, we see two different frequencies. And this frequency is much, much larger than the frequency of the diamagnetic that you see here. When you put gold nanoparticles, the only frequency that you see is this diamagnetic, which oscillating at much lower frequency. So it's very easy for us to distinguish a free radical from a diamagnetic signal. When we use low concentration of nanoparticles, we start seeing this, but it relaxes very fast. At the higher concentration of nanoparticles, we don't see the muonium. The only thing is the diamagnetic frequency, which is much lower. And when we go to higher temperatures, this effect is reduced. So that means what we are seeing is more important at low temperature and not high temperature. So because the rate constant was huge, close to 10 to the power 15 per mole per liter per second, experimentally based on what we observed, and because of the temperature dependence, we suggested that this is due to reaction with pre-solvated electron, not solvated electron. Of course, we could be wrong if the solvated electron reacts extremely fast with these gold nanoparticles. But basically what we see is that in these competitions of that involve in the radiation track, this is blocked and this is blocked whenever you have gold nanoparticle, and this is blocked at lower temperatures. At low temperatures, this is the winning reaction. At high temperatures, you actually start seeing some of these. But this is indirect because we could never see electrons, observe electrons, using the Muon methods. Now I'm going off topic for a while from the gold. I want to show something also that Cecile has done here on nanodiamonds. She has worked and showed that the OH overproduction for certain nanodiamonds with protonated, let's say, and the oxygenated nanodiamonds have actually lower production of the OH. And I get back into these later to make the correlations, although it won't be direct correlation. So a few interesting things here. She showed that as you increase the concentration, you see more OH production, and then you saturate the system. And there is significant effect of the surface, what you put on the surface on OH production. So this was in 2017. So we did some experiments with gold nanoparticles. I'm not going to describe a list because Mehran already described. And we showed that here we observed directly the electrons. And we see a spectrum very similar to a spectrum of the solvated electron in water in the presence of the gold nanoparticles at different time. We did experiments with the salts with a low concentration of the ionic liquid that we use as surfactant, and with the gold nanoparticle. And we see the yield of electron actually decreasing. This is aligned with what we have observed in the case of the Muon studies. Two very different techniques. This one, we did it at different wavelengths. The most reliable ones, which I'm going to describe why, is 780 nanometers that I'm showing. And in the IR, we showed the same thing. We did some work at higher concentrations that I'm not showing because now we know that at higher concentrations there are some problems with the optical spectroscopy method that we are doing here. But what we understand from this is that either the gold nanoparticle is not a radiosynthesizer or it is which is it could be a radiation shield, or if it is a radio synthesizer, because it reacts extremely fast with electrons, you end up having holes, H2O plus, in the system. And that H2O plus then generates OH radicals, and then you have a large concentration of the OH radicals in surrounding around gold nanoparticles, and therefore that would be the mechanism for radiosensitivity of the gold nanoparticles, most probably not generating excess electrons. Because we never observed, anyways, in any of our experiments, we never observed excess electrons. We always observed less electrons than we had, electron yield. Now, we did lots of experiments, we encountered problems, and we're learning from these problems. So when we go to 700 nanometer, the yield seems to be actually larger than when you do 780 nanometer. And the only thing that we could actually reproduce in the IR was around 780 nanometer results. We moved to the work that Slava did on gold nanoparticles made with PVA, with different concentrations, with different sizes. We were very happy that we are seeing these dramatic effects on the yields, but soon, not soon, recently actually, Sergey did some experiments on just pure water and putting filters in front of the water, in front of the water as compared to the reference. And as he decreased the number of the photons, he saw reproduce the effects that we were seeing with higher concentrations in the case of Slava and some of the other things we see in the UVs. So basically what it shows is that the IR set of data is much more reliable than the UVs, or we need to use a larger amount of photons to prevent this happen, which we are doing that at 780 nanometer. That's why I told you that I trust the data that we got here in the IR region and the 780 nanometer, but not the other wavelengths. So this is, I think, important. We are trying to find how to solve this systematic error. This is partially due to, if I understand it right, due to the lack of proper coincidence of the different beams. But we also see reactivity with the solvated electron, and we just recently did something that I think we can trust even the UVs, the reactivity of the solvated electron, which is extremely fast, even for gold nanoparticles. So this is the 95 nanometer at a very low concentration for reactivity of the solvated electron. So the same thing, we did experiments with nanodiamonds because we saw those effects, but I'm not showing those because we need to reproduce some of the results or just use the IR data. The palladium also showed significant effect in the visible region. These percentages that you see at 700 nanometer, all of them would become half. So we see 10%, or example, 13% and 20% for 100 nanomolar and 150 nanomolar. This is, although this is the atomic concentration, the real concentration, particle concentration, is picomolar for these particles. When we look at 780 nanometer, this is around 8% and 10%. So, and the same thing we observed in IR. So based on consistency of IR and the 780 nanometer, I would say these would be much less than what we have here. So around 10% efficiency in reaction with pre-solvated electron. Now, the other aspect is what is the role of nanomaterial at low concentration in other aspects of the charged nanoparticles. So when you have a charged particle with high speed in a fluid, you get sharper thermalization at higher density and diffuse range at lower density. We use this very often, for example, at TRIUMPH or at other particle accelerators to study high pressure versus low pressure related to the nuclear reactors. We don't expect a significant role, although for the high density or low density change of density on interaction with the nanomaterial. Another aspect of the charge interactions with matter is that it leaves track of ionization in matter. I think we showed from the data that I showed you that indeed we can affect the track with the nanomaterial. So interface of nanomaterial with liquids would affect the track. Now, sometimes depending on the charge that you are using, you also generate Cherenkov radiation. Again, Mehran showed you a picture of that. The other question we had, could Cherenkov radiation be affected by the nanostructure in the fluids? And would it be dependent on the chemical environment? And could it be used, therefore, as analytical method to probe inside nuclear reactors, for example, or inside radiation therapy in body to get chemical environment? Quick information about the Cherenkov radiation is a coherent light with incoming charge with very fast particles. So usually this happens whenever the velocity of the phase velocity in the medium would be of the light would be less than the charged particle velocity, and there is a threshold of 1 over refractive index to see this coherent picture. So light going from here to here, and the particles going from here to here, and you get an angle based on this classical wave effect. Now, I'm completely ignoring the quantum effects in this, and this is purely classical, what I'm showing you. What would be the interface of the nanomaterial and liquid on Cherenkov? So the velocity of light first must exceed the phase velocity. And the phase velocity, we know that can be changed noticeably in a periodic medium. There are papers, lots of papers that show that. Can a liquid be considered with the nanostructures in it, a periodic medium? How about an ionic liquid, which we know they form different structures, nanostructures of the periodicity? Now, if that's the case, and if we can achieve the Cherenkov radiation, in these cases, there are even, in the case of the solid at this state, cases that there is no minimum particle velocity. And this phenomenon is observed by Smith and Parcel, so it's called Smith-Parcel effects. And there are many reports of more complex periodic mediums on the Cherenkov radiation that they completely change the Cherenkov radiation. So how would environment with nanostructures in the fluid affect the Cherenkov radiation? This is the work that mostly Alec is doing right now. He's preparing samples for the experiments we are doing later also today. And I'm showing these data just recently, some of them when I got them today. From him. So these are very fresh data. This shows the water Cherenkov, the blue, and then you have ionic liquid at very low concentration. Sorry, gold nanoparticle has very low concentration, 16 picomolar to 100 picomolar range. And you can see that at higher concentrations, you see significant difference, even at very low concentration, significant difference between the water Cherenkov and Cherenkov that we get from the gold nanoparticle solutions in water. Of course, there are lots of optical effects that we need to correct for. a scattering of light, absorption, in addition to excess Cherenkov. So these are all things that Alec needs to work for a while. Then we go to nanodiamond, and we see opposite effect to the gold. We see enhancement in the Cherenkov radiation at micromolar concentration. Although we see even a larger effect when we go to the very large nanodiamond in water, but at extremely low concentration, so sub-picomolar. And also we put then two ionic liquids. Now, remember I told you the refractive index is important, right? We have this ionic liquid and the other one. The molecular structure of the anion is different, but the refractive index of them is almost the same. So, and they are purely ionic. They have the same concentration of ions. You would expect that the Cherenkov that you get out of them would be the same if it behaves on the classical. The number of the so water is the black in this and blue in this one. The number, you can see that the number of the photons that we get from the Cherenkov is hugely different between these two. The only difference is the molecular structure of the anion of the two that we are getting. And we did it in the kinetic mode, so we can actually see the damage that is happening by radiation with each shot. So this is the original one. As we go, this one goes upward. Sorry, let me go back. This one shift to the left and up. This one shift to the right and down. Very different. I mean, we don't understand yet why, but it shows that we can use actually Cherenkov to get the radiation damage for, and we are planning to do that for the hopefully nuclear reactors and also the molten salt-based nuclear reactors. So what did we learn from this study of nanoparticles so far? Different nanocrystalline material structures react with electrons. Some potentially before electrons can get solvated. The preliminary IR data suggests the following: that palladium is more than gold efficient, and then silver, Fe3O4, nanodiamond, and zinc. So far, it seems the larger nanostructures are more reactive towards the electrons, but we need to do more experiments to understand and show this. The observed Cherenkov from samples is significantly affected by nanostructures. Solvent with very different dielectric properties, very similar dielectric properties, with different molecular structures have different Cherenkov spectra. Maybe one of the most important things is that, based on work that Sergey did, we discovered the problem with the visible system in ELIS. And this would be extremely important for the people that I think do solid states work. I think it's important to use complementary techniques for scientific problems. Here we do IR versus the visible, and that would show the artifacts that we get under conditions, or even when you compare with the Muon experiments and the electron experiments. Some questions that we have: what is an, for me at least, what is an electron with kinetic energy larger than thermal liquid, like in water? Should it be treated as a wave or particle before interaction with nanoparticle? So I'm talking about the electron volt energy, electron or less than kV electron volt, kV. Is the capture of electrons by nanoparticles at picomolar to nanomolar, so we are talking about very low concentrations, do they need contact with the, even if we consider solid electron? Or can they be captured at 1 to 100 nanometer in liquids by quantum tunneling? I don't have much time to go to the weak external field interaction with nanocrystal, so I quickly show you some of the work that we did with the sensor design. So basically, we have indium tin oxide. We did different grow different metal oxides on indium tin oxide with gravity. Direction of the gravity is, let's say, in this direction, so we call it plus z, k direction, and with different magnetic fields. We do it in a strong field, low field, as we move it through a magnet. What we showed is that when you do these experiments with metal oxides on the surface of indium tin oxide as the substrate, these are all with the same dimension of 1 micrometer as the slides show. We show extreme effect on the morphology by just applying gravity inverse or with gravity and with magnetic field. And the most important thing is the actually vector direction of the magnetic field relative to the gravity with respect to the crystal growth. This is for metal oxides that are non-magnetic, supposed to be non-magnetic, like zinc oxide. Quantitatively, we see that with the magnetic field, for example, gravity, we can change significantly the dimensions, both the length and the diameter of the nanomaterial. But when you look at the chemistry, there is no room for any paramagnetic species in the chemistry of making these. We do it under hydrothermal conditions. So where does this magnetic effect come from? We did lots of magnetic susceptibility. We showed that the nanomaterials are paramagnetic actually, and then at very low temperature they become more like ferromagnet. And remember, these are zinc oxide. Then we did the fluorescence experiments on them, and we see that depending on the morphology, we also see different fluorescence, and this fluorescence at around 650 nanometers is associated to the defects, and these defects are moved zincs from the lattice, so that you have vacancies of zincs, and therefore you have paramagnetic property because of these oxygens. And important is that these fluorescence would decrease as we increase the length divided by the diameter. And we can actually change all of these by direction of magnetic field relative to gravity. Now, why we did that? We have because we wanted to see if we can use this as sensor. So we put bacteria on them because it's very important to detect bacteria in the solid state, not to take it to the lab and do all the biochemistry work. We wanted to see if you put it in a solid surface in hospitals or in packaging, you put a small device here and you measure the electrical properties of these based on exposure to bacteria. So we did lots of microscopic measurements and then electronic resistance basically measurements for different bacteria with different bacteria and different fungi, and we showed that based on the comparison with the control, we have a significant effect of bacteria and fungi on the conductivity of these. This is already patented, and I'm getting lots of industry interest to collaborate in this direction. So we did also some control on the growth of bacteria. We found that in indium tin oxide alone, you get very similar to the growth you expect on a glass, but when you put zinc oxide on it, the growth gets inhibited. And the surface resistivity doesn't change with exposure to the bacteria for the case of indium tin oxide, but for zinc oxide on indium tin oxide, it would significantly change. And from the time dependence of these, we can actually detect based on different morphology, which we can apply based on the effect of the magnetic field and gravity, detect different bacteria and fungi. So some observations here, the growth of zinc oxide and other metal oxides we have done can be controlled using a combination of low magnetic field. We are doing everything less than 1 Tesla here, or less than 0.5 Tesla actually. And this control affects the ability of nanocrystal relative to response to the pathogenic bacteria and fungi. I think one that is very interesting is that the let's call the gravity field G, this G dot B over GB is important. So the direction is extremely important for the growth. But at the same time, this means this affects the atomic displacement in the metal oxides. And atomic displacements are governed by potential energy surface of the atomic interactions. So does that mean that we actually need to bring something like this in the Hamiltonian of the systems because they generate defects? So these are the things I want to know. I want to thank again all the members of the ELIS. Thank you very much, and everyone here, and also for the invitation. Thanks.
Muon setup. So how is it done exactly? You have both electron and muon beams?
No. This is the electron beams were done here. The muon beams were done at different accesses. We did at Triumph in Vancouver and Rutherford Lab and Japan. So the reason you saw those electrons in the muon is that any ion, when it's high energy, when they come in sample, they generate electrons because of ionization. Yes. Yeah. But the direct electron effects, that's why we came here to see it.